About learning target 6B part 1, which has to do with simplifying radicals using multiplication and division of radical expressions. So by the end of this lesson, you will be able to multiply radical expressions and simplify, as well as divide radical expressions and simplify. So when we're talking about multiplying or dividing radical expressions, this is only possible to do if So notice in our theorem that we have here, we have the nth root of a and the nth root of b. We're going to assume that both of those are real numbers. Then we are able to multiply the nth root of a times the nth root of b here, assuming that both of them are the same nth root, meaning they would both have the same index of n. And when we do so and we multiply them, what we do is we're multiplying the two radicands. So in our first radical expression here, a is the radicand, and in our second one that's being multiplied, b is our radicand. Because they have the same index here of n, we can multiply them together and we get the nth root of a times b, where our new radicand becomes the product of our prior two. Similarly, if we have division and we have the nth root of a divided by the nth root of b, because they have the same radicand, we can simplify that as the nth root of the entire fraction of a divided by b. Now, because we're dealing with division here, we do have to make the assumption that b is not equal to 0, otherwise we're going to get an undefined expression. Again, this only works when we multiply or divide if they have the same index overall. Let's start looking at a couple examples. In these examples, we want to simplify them completely. In our first example, we have the square root of 8 times x to the 5th times the square root of 3x. In this case, both of these are square roots, so they both have an index of 2. Remember, our index is that superscript in front of the radical symbol, and if there's no number there, we denote that as a square root, so our index would be 2. In this case, they both have the same index, so we are able to multiply these together. And so this is going to be equal to, all underneath a single square root, the 8x to the 5th times the 3x. Now in this case, we can multiply the coefficients. 8 times 3 would give us 24. And we can combine the x to the 5th times the x to the 1st, because those are like terms. X to the 5th times x to the 1st, because they have the same base, we would add the exponents, and we will get x to the 6th overall. This now looks similar to a problem that we would have seen in learning target 6a. In this case, we can continue to simplify here, and we can break apart our radical again and take the coefficient piece, so take the square root of 24, separate from our variable piece with the square root of 6. Now the square root of 24 is not a perfect square, but 24 does have perfect square factors inside of it. On the side here, I'm going to do a factor tree for 24. Why don't you guys pause the video right now and think about what perfect square factor is a factor of 24. So 4 would be our perfect square factor that we have of 24, and 6 times 4 would give us 24. So when we take the square root of 24, that would be the same thing as taking the square root of 4 times the square root of 6. In this case, since 4 is a perfect square, the square root of 4 would give us 2. And the 6, since that has no other perfect square factors and is not a perfect square itself, is still left inside the radical symbol here. So we end up with 2 times the square root of 6 coming from the square root of 24. Now, to simplify the variable piece of this, we're going to do the same properties that we learned in learning target 6a. So we know, and as a little review here on the side, we learned in learning target 6a that the nth root of x, if we want to convert that to exponential form, would be equal to x to the 1 over n power. And we're going to keep using this same idea throughout the rest of this unit, as well as our next unit actually, to help us solve and simplify radicals. So again, the nth root of x is the same thing as x to the 1 over n power, and that is giving us our exponential form. So in this case, our square root would be the same thing as the 1/2 power, because 2 here is our index. So we end up with x to the 6th to the 1/2. Using properties of exponents, if I have exponent raised to exponent, we can multiply them. And so if we multiply 6 and 1/2 together, we're going to end up with x to the 3rd. Now in this case, something else that comes up from learning target 6a has to do with those absolute values. And in this case, because our index was 2, that is an even number, so we do have to worry about absolute values in this case. So I will end up with actually 2 times the square root of 6 times the absolute value of x to the 3rd. Now, we do want to consider if we can ever remove the absolute values if their term itself is already positive. But since we don't know what x is, and if x is a negative number, then any negative number to the third power would still be negative. So we need to keep the absolute values around that x to the third. And that right there is going to be our final answer for problem 1. Okay, let's take a look at problem 2. So why don't you guys pause the video right now and determine what the index is for both of those radicals. So in problem 2, our index is going to be a 2. We have 2 square roots again, and in this case we're seeing the division that's happening. So we have the square root of 18x to the 5th divided by the square root of 2x to the 3rd. Now we can simplify that under one square root because they have the same radical, and we'll have 18x to the 5th divided by 2x to the 3rd, all underneath the same square root. In this case, we have quite a few like terms that we can start simplifying down. So 18 divided by 2 would give us 9. And x to the 5th over x to the 3rd, since we have like bases here, we can subtract the exponents, where we take the numerator minus the denominator. So we're going to end up with x to the 5 minus 3rd power, which would give us x to the 2nd. Again, just like we did in Learning Target 6a, this becomes a problem that we've seen before where we can start simplifying it by breaking it apart to the radical piece, or I'm sorry, the coefficient piece as its own square root, and then the variable piece as another square root. Here, the square root of 9 is a perfect square, so we're going to end up with 3. And the square root of x squared, we can again transform that from the radical form into the exponential form by rewriting the square root as the 1/2 power. When we multiply those, we end up with x to the 1st. We do have an even index here, so we have to consider absolute values. So technically we get the absolute value of 3x, but in this case we can take the absolute value of 3, so the 3 would come outside of the absolute values, and then the absolute value of x is still, or the absolute value is still left around the x, since we do not know if x is positive or negative, and if x were a negative number, we would need those absolute values to turn that into a positive. Okay, let's look at example 3 here. So in example 3, we have the cube root of 4x to the 7th times the cube root of 2x squared times y to the 12th. Why don't you guys pause the video here and determine what your index is. So for both of these radicals, our index is a 3 since we have cube roots. Because we have the same radicand though, or same index, we can multiply the insides together. So we'll end up with a cube root of this whole product multiplied together. Now 4 times 2 would give us 8. X to the 7th times x to the 2nd, because they are the same base, we can add the exponents and we will end up with x to the 9th. And then the y to the 12th, there's no other like term that would be able to combine with, so we still have that y to the 12th. Now from here, we can again break this apart, and we can also convert from radical form to exponential form. I'm going to do that in one step by rewriting this as the cube root of 8 for the coefficient piece times x to the 9th, y to the 12th, all to the 1/3 power using that cube root. Since our index is 3, that becomes 1 over our index, so 1/3 becomes our power. Now from here, we have quite a bit of simplifying we can still do. The cube root of 8 is going to give us 2. And for each of these bases, we can actually distribute that exponent using another properties of exponents. So we end up with x to the 9th to the 1/3, y to the 12th to the 1/3. And from there, we can continue to apply properties of exponents by multiplying our exponents. So x to the 9th to the 1/3, when those get multiplied, gives us x cubed. And then the 12 times the 1/3 would give us y to the 4th. Now, do we need to consider absolute values in this case? What do you guys think? In this case, since our index is 3, that is an odd number, so no absolute values are ever considered. So this would actually be our final answer overall. Okay, let's look at our 4th example. Here we're going to start to see a little bit of more steps getting layered in. So in example 4, we have 4 times the square root of 2x times 5 times the square root of 6xy squared. Why don't you guys pause the video right now and determine what your index is. So for both of these, we have square roots. So our index is going to be 2. This means that index is even, so we will want to consider absolute values at the end of this problem as we start to simplify. The other thing that makes this problem different than any other previous problems is the fact that they're actually coefficients outside of the square roots themselves for both of them. What do you guys think we're going to do with the 4 and the 5 that are outside the square roots? In this case, because everything is being multiplied together, we could rearrange this multiplication, because multiplication is commutative, and we could rewrite it as 4 times 5 times the square root of the 2x times the square root of our last radical. In this case, we can see that 4 and 5, because they're both outside of the radicals, we can actually combine together and multiply those, and that will give us 20. Because each of these are the same radical, we can also continue to combine those together because they each have the same index of 2, and we'd end up with the square root of 12 from the 2 times the 6, and then the x times the x are like terms, so we can add their exponents and get x squared, and then we still have that y squared as well. From here, we want to continue to simplify this just like we've done other problems. Why don't you guys pause the video right here and try to simplify this on your own, and then we'll check our final answer together. So our first step in wanting to simplify this is we do want to simplify the coefficient piece. So the 20 is going to go along for the right. It's still going to be multiplied. We're going to have to come back and simplify the square root of 12. And then I'm also going to rewrite the variable piece already to the 1/2 power by using that index and converting from radical to exponential form. Now from here, if we want to simplify the square root of 12, it's not a perfect square, but 12 does have perfect square factors inside of it. 4 would be that largest perfect square factor, and 4 times 3 would give us back to 12. In this case, when we take the square root of 12, it would be the same thing as taking the square root of 4 times the square root of 3. Since 4 is a perfect square, we can simplify that. Now remember, we still have the 20 from the original problem coming from that 4 times 5. We now also have a 2 outside of the square root from the square root of 4, and then the square root of 3 is still going to be left over inside. Now in our last two terms, we still have the x squared to the 1/2 as well as the y squared to the 1/2 that we'll need to simplify. Both of those we can multiply the exponents together to get 2 times 1/2, which will just give us x to the first and then y to the first as well. I've also multiplied out the 20 and the 2 because they are both outside of the radical. So we ended up with 40 times the square root of 3 and then the x times the y. Again though, since this index is even, we do have to consider absolute values. So technically the whole thing gets absolute values around it. In this case, the 40 and the square root of 3 are both already positive, so we can take those out of the absolute values. The x and the y though, since both of their powers are odd, we need to leave them inside the absolute values because x and y could potentially be negative. And that right there would be our final answer. Okay, let's look at our fifth example. So here we have 3 times the square root of a to the 5th times b to the 3rd times the square root of 4a squared times b. Now, why don't you guys pause the video here and start to simplify this down and combine it into one radical together, and then we'll check that step. So from here, because they're both square roots, they both have an index of 2, so we can combine them together. The 3 will stay out front. There's also an invisible 1 in front of the second radical, so 3 times 1 would still give us 3. We now get the square root of 4, and then the a to the 5th times the a squared can simplify to be a to the 7th. b cubed times b would give us b to the 4th. Now in this case, we want to continue to simplify just like we've done. So I'm going to break this apart into the square root of 4, and then we have this a to the 7th. Oops. There we go, an a to the 7th, and then the b to the 4th, all to the 1/2 power. Now 4 is a perfect square, so let's go ahead and simplify that. So we get 3 times 2. We also have this a to the 7th to the 1/2, and then this b to the 4th to the 1/2. Now, as we continue to simplify the variable piece, we'll notice that 4 times a half will give us an integer value of 2, but 7 times a half is going to leave us with a fraction still. Now, when this happens, we need to think about what is our largest number that is less than our power of 7, that is divisible by 1/2, and we're going to want to kind of break apart or peel apart the a to the 7th as a to something times a to something else. Now in this case, 6 is a number that is smaller than 7, but is now still divisible, or is now divisible by 1/2. So we're going to actually break apart the a to the 7th as a to the 6th times a to the 1st. And the reason this works is we're ultimately using properties of exponents, but we're just expanding it out instead of condensing it down. So our a to the 7th itself came from the a to the 5th times the a squared, which we added together to get the 7. But we can also break apart 7 as 6 plus 1, so we can split that apart into a to the 6th times a to the 1st. And again, the reason this is helpful is because a to the 6 is now divisible by, or 6 is now divisible by 2, so we're going to actually end up being able to simplify this. And for this leftover a to the 1st, we're actually still going to have a variable left inside our radical. Now, we haven't seen this yet because all of our examples have been perfect factors of our indexes for the variable exponents, but it is possible to still get variables left inside the square root, cube root, or whatever nth root we might have. The other piece we do want to make sure we're continuing on with this problem is the b to the 4th to the 1/2. That is going to be perfectly divisible, so we're getting b to the 2nd there. And then, I didn't say it, but the 3 times 2 is giving us that 6 that's out front. Now for the a pieces, I want to continue to simplify, so we get a to the 6th to the 1/2, and then we have this a to the 1st to the 1/2. We still have the b squared. Now a to the 6th to the 1/2, when we multiply that, will give us a to the 3rd, and then a to the 1/2, or a to the 1st to the 1/2 will just give us a to the 1/2, but remember, if you have the square root of, let's say, x, that is the same thing as x to the 1/2 power. So I'm going to work backwards now and actually rewrite this as the square root of a. Because a to the 7th ultimately was not a perfect square, that's why we're still getting leftover variables inside of our square root. And then lastly, we still have the b to the 2nd. Now, one more layer on this problem, though, is because the index is 2, that is an even value, so we do need to think about absolute values. So in this case, technically everything that came out of the square root is inside absolute values. We can also leave the square root of a in there as well. But as we start to simplify this, 6 we already know is positive, so 6 can come outside of the absolute values. B squared itself is also always going to be positive, because no matter what type of number b is, positive or negative, when I square it, it will always come out positive. So leaving that inside the absolute values is a little redundant, which is why we can take it out of the absolute values, just like we can take 6 out of the absolute values as well. Now the square root of a is also technically not inside the absolute values at all, so I really have the absolute value of the 6 a to the 3rd, and then separately the absolute value of the b squared. So the square root of a is still there, but left over inside the absolute values is still going to be the a to the 3rd, because a, depending on what a is, if a is negative, a to the 3rd would still be a negative number. That right there would be our final answer. And we could start seeing more examples like this where we have square roots of variables left over, just depending on if that power was divisible by our index or not. And again, to reiterate, when the power is not divisible by the index, our goal is to find the next smallest number that is divisible by that index. So since 7 itself was not divisible by 2, but we can break apart 7 as 6 plus 1, and 6 is the largest number that is less than 7, that is also divisible by 2. That's why we want to use this break apart of 6 and 1, because that tells me that once I simplify down completely, the square root of a will be reduced down as far as it can. Another way to check that is if you still have variables left over inside of your radical, the exponent on the variable here, and our exponent on this guy would be the first power, has to be less than the index itself. So in this case, since we have a square root, our index is 2, and the power that we have left inside is a to the 1st, 1 is less than 2, so we know that that is simplified down all the way. If this was still an a to the 3rd, there's still more simplification that could happen because 3 is bigger than our index of 2, so there's still more perfect square factors that we can take out of that. Alright, let's look at example 6. Why don't you guys pause the video here and decide what your index is. So in this case, we have an index of 3. For both of these, we have a cube root of 48x to the third y squared and the cube root of 6x to the 6 times y. Because we have the same index, we can actually rewrite this as one gigantic cube root of the 48 x to the third y squared over 6 x to the 6 times our y. In this case, we can continue to reduce stuff down. 48 divided by 6 would give us 8. X to the third over x to the 6 would give us x to the negative third, because we can subtract those exponents, or we always take the numerator minus the denominator. So 3 minus 6 would give us negative 3. And likewise, we can simplify the y's by going to minus 1, which will give us just y to the first then. And all of that is inside our cube root that we have. Now from here, there is more simplifying that we can do, but we can't simplify stuff with negative exponents. We're going to want to rewrite that right away. So we're actually going to flip that down, and the x to the third, to make that a positive exponent, will go down to the denominator. The 8 and the y are going to stay in the numerator because neither of those have a negative exponent. So both of those stay in the numerator where they were to begin with. And from here, we want to kind of break this apart into all of our pieces. So we have the cube root of 8 times the cube root of y all over the cube root of x cubed. Now, 8 is a perfect cube. The cube root of 8 is going to give us 2. Now, the cube root of y, if we were to rewrite this as the 1/3 power, we'd have y to the first times the 1/3, which are not divisible by each other, and 1 times 1/3 would just leave us with 1/3. So in this case, the cube root of y is as simplified as it possibly can be, and another way to check that is that the power here that's inside our radical is less than the index itself. So since we have a y to the first and 1 is less than 3, that is simplified as far down as it can be. But the cube root of x to the third can continue to simplify, so we can rewrite that cube root as the 1/3 power. We can multiply those and get our 2 times the cube root of y all over x. Now, do we need to worry about putting absolute values on anything in this problem? In this case, no, we do not. Our index here was 3 again, which is odd, so there are no absolute values needed. There's no reason to even consider them, and that would be our final answer. Okay, let's look at our next example. So in example 7 here, we have the cube root of x times the square root of x. Why don't you guys pause the video right here and determine what our index is. So in this case, we actually have an index here of 3 in the first problem, or in the first radical, and then for our square root, we have an index of 2. So in this case, if we're going to leave it in radical form, there is no way to simplify this further because the indexes are different. So again, if we're going to leave it in radical form, we cannot simplify any further because we have different indexes. Now it is possible to rewrite these both in exponential form, and we could rewrite this as x to the 1/3 times x to the 1/2, and then because we have the same base, we could actually add the exponents together and get it to be a single x to a power if we wanted to write in exponential form. But if we're trying to leave this as a radical, there is no way to simplify this any further on problem 7. Let's look at our last example with problem 8. So on problem 8 here, we have the cube root of a times the cube root of b squared. Pause the video right now and decide what our indexes are, or maybe if we have two different indexes again. So in example 8, we have a singular index for both of them. They both have an index of 3. So in this case, we are able to simplify these together because we have the same index, so we can multiply the a times the b squared. Now, a and b squared are not like terms because they're different bases, so there's no way to combine those together using properties of exponents or at all. So we're left with just a times b squared. And now we want to think about if we can simplify this down anymore. What do you guys think? Can we simplify this down any further and take anything out of the cube root? In this case, we're not able to. Both of these powers, so we have an a to the first and a b to the second, both of our powers of 1 and 2 are less than our index of 3, so there's actually nothing that we can do to simplify this down, and that would be our final answer overall. And with the a to the first, we can either write the first or you can just leave it as a. But again, both of those powers of 2 and 1 are less than our index, so we are done simplifying as far as we can. And I want to leave that here as kind of a side note for this whole video. We know that we are done simplifying when our power is less than our index. And that will be a good way to always kind of check and make sure that we have simplified down all the way. Now that is the end of Learning Target 6B Part 1. So in this video again, we discussed how to multiply and divide radical expressions, and this only works if they have the same index. In Part 2, we're going to talk about how can we add and subtract radical expressions together and what is necessary for that to occur.